Hello everyone, and thank you for coming to view this presentation. My name is Brendan Zember, and I'm a fourth-year computer science and math major here at Eau Claire, and today I'll be talking about cyclic redundancy checks. To start out with, I'll be giving an overview of what a CRC, or cyclic redundancy check, is, and then I'll be going into some of the math that drives the process before moving into describing fully what the algorithm is itself. To wrap it up, I'll be talking about generator polynomials, which you'll be understanding more about very shortly. So, cyclic redundancy checks deal with how do we send information and be sure that there are no errors that happen when we send that information. How do we know for sure when we receive something that we're receiving what we're meant to receive? So if I want to send a message K, the computer breaks that message down into binary. It's a string of ones and zeros called bits. And it's possible when I send that information that there will be an error along the way. Maybe there's a bit of a magnetic impulse. Maybe it's a cloudy day. Things happen. And it's possible that the message may arrive with a bit flipped. And that can completely change the concept or the meaning of the message that is being sent. Obviously, this is an issue, and we want to prevent this. And that's precisely what CRCs do. It is a way of detecting errors in a transmitted binary message, in a text or a streamed video, or even communications on hardware levels. It's a way of making sure that the information that arrives is the information that was sent. And the way this is done is it utilizes polynomial division over a group of these ones and zeros, of these bits. And it manifests itself in just simply sending a couple more bits along with the information that you were able to send. And those bits tell the receiver everything they need to know on whether or not they're receiving the correct information. So before we get into the algorithm itself, we need to define more what binary is. So we have the Galois field of order 2. It's a fancy way of saying is that I have a couple of numbers that I can do stuff with. I have a finite set of numbers, 1 and 0, and I can add and multiply them. And specifically, these operations are laid out in that table there. It's a nice and small table because we only have 0 and 1 as our possible numbers. So addition is defined as something that's called the XOR operation in computer science or with logic. Our result of this operation is 1 only if just one of our parameters is the value 1. So if we have 0 plus 0, there's no 1 in there, so we have 0. If we have 0 plus 1 or 1 plus 0, then there's just 1 in that operation, so we end up with 1. And then 1 plus 1, we don't have just 1, so we end up as 0 for our result. Similarly, for multiplication, we have that the outcome of this operation is only going to be 1 if all of our parameters are also 1. Otherwise, we have 0. Now that we have an entire field defined on ones and zeros on a single bit, we can string together bits by taking the polynomial ring over the Galois field of order 2. So this allows us to have entire strings of binary data, and these pieces of information can also be represented as polynomials, where, since we're over the Galois field of order 2, the coefficients can only be 0 and 1. So if we have a binary string of 1, 0, 1, those ones and zeros represent the coefficients of individual monomials that make up the larger polynomial. So for 1, 0, 1, we have, looking at the farthest rightmost bit, we have 1 for x to the 0, 0 for x to the first power, and 1 x squared power. And so this simplifies, obviously, to x squared plus 1. Now we can do addition with these binary strings as well, and that is just the same for individual monomials as the addition operation that we just went over for the Galois field. And so, as we'd expect with the polynomial addition, this translates to the binary string addition as well, where when we have 1, 1, 0, 1, adding it to 1, 0, 1, 1, the farthest rightmost bit has 2 1s, so we end up with 0. The middle 2 bits have just 1, 1 for their respective indices, so we have 1 and 1 for the middle bits, and then same thing for the farthest leftmost bit, where we have 1 plus 1, and so 0 for that x cubed monomial. And now we can get into exactly what a cyclic redundancy check is doing. So it's a very simple process, all things considered. First, the sender and receiver must decide on a single polynomial called C. It's a generator polynomial. And this single polynomial is going to be very important throughout this whole process, which we'll get into a little more at the end of this presentation. After we've decided on a polynomial, we have to add a couple more empty bits, 0 bits, to the message that we want to send. And then, now that that message is a little larger, we can do long division with that lengthened message by our decided upon polynomial C and get the remainder of that operation. Lastly, we subtract that remainder from our lengthened message, which will allow us to have a result that is divisible by our generator polynomial. So, say for example, we want to send just the letter K. As stated before, this can be broken down into a binary string, which is the same thing as our polynomial x to the 6th plus x cubed plus x plus 1. So, for step 1, we want to decide on a polynomial. For this example, we're choosing 1, 0, 1, 1, or equivalently x cubed plus x plus 1. Note that the largest order monomial in this is x cubed. And now, since we have 3 there, that is how many bits that we are adding to our message m. We are lengthening it by 3 positions. Now, in terms of binary operations, this is accomplished by just doing a left shift by 3 bits. But in the polynomial representation of this is the exact same as multiplying our polynomial by x cubed. Now that we have this lengthened message, we can do step 3 and divide out our message by our generator polynomial. Just like the long division that you're familiar with and already love so much, whenever you have a 1, whenever our polynomial can divide into the larger message, that is when we subtract out the polynomial and follow through with that repeated process, ending up with a remainder of 1, 0, 0. If you want to pause the video here and walk through this long division too, I would recommend that. It really helps to cement in the algorithm. So then, performing this long division, we have a remainder of x squared. And now we can subtract this value from our original message and end up with a value that is perfectly divisible by our generator polynomial. So the beautiful thing about this is that subtraction and addition in our field is the exact same. And so really we're just taking our original message, adding on a remainder, just shoving it onto the right of that message, and then sending that. This value is exactly what is sent to the receiver whenever you're sending a message or receiving a stream of data. This is the exact process that happens. And so the receiver then gets this transmitted message and performs the same long division by that agreed upon generator polynomial. If it divides perfectly, then they can be reasonably sure that there were no errors in the transmitted message. Otherwise, if there was a remainder after performing this operation, they know for sure that there was an error that occurred, and then they simply ask the sender to resend that same information so they can get the proper intended message. And then to receive the original message from the altered message, all they have to do is subtract out that remainder, which is the last 3 bits, and then divide by x cubed, or equivalently shifting the entire message to the right by 3 bits. And then this value is the intended message for the receiver. So now say that there was an error in the message. There's a bolded 1 there in the message there at the top, where we have a 0 that was flipped to a 1. Now when we perform this long division, as you can see, we end up with a remainder of 1, 1, 1, x cubed plus x plus 1. This obviously is not 0, and so we know that C does not divide the received message. And so there was for sure an error that occurred. Now, something peculiar that I mentioned earlier, I said the receiver can probably be sure that the message they received is correct if their generator polynomial divides the message. And this isn't an exact assurance. They don't completely know that the message has no errors, and you'll see why with this. When we have when we're receiving a message, really we are receiving the original transmitted message plus any possible error that occurred. And so simplifying that out, expanding that out, when we perform that long division, we have the intended transmitted message plus that error polynomial divided by C, and we can break that up as using properties of division that we already know. We know that C divides T. That's the whole point of the transmitted message. But the point of the generator polynomial is to make sure that chances are C will not divide E. But how can we be sure of that? We can use elementary number theory and simple brute force calculation to be sure that probably we will be able to detect any errors when we divide by C. So for example, looking at that error polynomial a little more, if there is 1 bit that was flipped, there's just a single polynomial that exists, single monomial that exists in that error polynomial, then it is represented by simply x to the ith power. It's just some bit that exists. Now, to be able to detect that with the generator polynomial, all we need is x to some power plus 1. We know that x plus 1 will never divide x to some power. And this exact polynomial, x plus 1, is exactly what is used in a lot of communications. It's very cleverly named CRC1. It's used in a lot of hardware communications. Similarly, say that there are 2 bits that are incorrect, then our error polynomial is x to some power plus 1 plus x to that same power. And simplifying that out, we see that there are 2 factors in this error polynomial. One being one that we've already seen, x to the ith power, and then another one, x plus 1. Now, we can choose the same polynomial, x plus 1, and we know obviously that this doesn't divide x to the ith power, but it does divide x plus 1, so we can't use just x plus 1 as a generator polynomial and be sure that we will catch any possible error, because if there are 2 bits in a row, we won't be able to detect it, because we will still divide perfectly into E. But this is easily fixed by just choosing x to some power that is not 1 plus 1, and we will still be able to detect that error. Now, using nice properties of the polynomial ring over the Galois field of order 2, this one is a little more complex, but if our generator polynomial has one of its factors being x plus 1, then as we expand out our generator polynomial, as we multiply the rest of C by x plus 1, we're going to always have an even number of terms. And there's an even number of bits in our generator polynomial. And so, we, using this knowledge, can know that if there is an odd number of incorrect bits in E, then C will never divide E. So for choosing a good generated polynomial to decide upon, all we need to look at a lot of errors, at least half of any errors that may occur, all we need is x plus 1 to be a factor of our generator polynomial. From here, there's a lot of just brute force calculations of I'm going to pick a generator polynomial that has x plus 1 as a factor, and then calculate every possible error that could occur and see if this polynomial divides it. And we are able to come up with a lot of good options for generated polynomials that work for most cases of errors that may occur for 1 bits, 2 bits, 3 bits, 4 bits, etc. Specifically, some of these have more creative names. We've seen CRC1 already, which is just x plus 1. It's also called the parity bit. If there's an odd number of 1s in our message, then our remainder is simply going to be 1. If there's an even number of 1s in our message, then our remainder is going to be 0. This exact CRC is used in hardware communications. Whenever there's a message being sent along in your Alexa or in your calculator, there's one extra bit that's being sent along to tell another component in that piece of hardware whether or not there was an error in the transmitted message. Similarly, we get more long and complex for our generator polynomials. The CRC8 is a polynomial which is used for a lot of video streaming and broadcasting, which has certain benefits to it, specifically for that medium, where if in video streaming we are more okay with poor quality rather than losing entire seconds or frames of video. And so this specific CRC is good for those types of errors. And then we see the CRC32, which is used a lot in Ethernet communication, and then also applied for PNG image formatting. At the end of every PNG file, there is a certain number of bits, 32 bits exactly, that is telling you if the image that you're looking at is corrupted. If your computer is not able to divide the bits of that image perfectly, taking into account the remainder at the end of that file, then it knows that you have a corrupted image and it won't be able to display properly. So that is the end of my presentation. Thank you so much for watching this, and I hope you all have a great day.